In this second module of Chapter 7 on extensions of stable population theory, Module 7.2, I will cover stochastic demography. Stochastic demography is concerned with the theoretical and empirical study of random variation in demographic rates and processes. Understanding the effects of stochasticity on the dynamics of populations is important for the simple reason that real-world populations of both humans and non-human species are subject to stochastic conditions. Thus, knowledge of the extent to which uncertainty affects birth, death, and/or migration rates is fundamental to demography in general, and more specifically to the formulation of population policies. Stochasticity may be introduced into population models in basically two ways. The first is referred to as demographic stochasticity. This concept of stochasticity differs from the concept of deterministic rates because in a deterministic model, each member of the population gives birth to a tiny fraction of an individual in each interval of time. But in a stochastic model, only whole animals are born with specified probabilities. A population goes extinct when its last member dies, and this death may be due to chance alone. Similarly, the population is reduced to its last member when its second to last member dies, and this death may be also due to chance alone. The central questions regarding demographic stochasticity have to do with the extent to which chance alone plays a role in population change. Clearly, at low population numbers, a single addition or subtraction event may have a substantial impact on the population. A single individual is a small proportion of a population of 1,000 or even of 100. However, this same individual is 10% of a population of 10 and 100% of a population of 1. When this one individual dies, the population is extinct. Thus, demographic stochasticity is especially important at low population numbers and where there is a high likelihood of extinction. The second way that stochasticity is important to population models is through environmental stochasticity. Environmental variation arises when the demographic rates themselves are externally driven by stochastic processes due to environmental randomness, such as bad winters or failures of food supplies. The basic distinction between demographic and environmental stochasticity is that the former arises from fixed vital rates, while the latter arises from vital rates that vary over time. Cohen in 1982 provides the following example to illustrate the differences between the two and their magnitudes in the case of mortality. Suppose for a population of n equal 1 million individuals that the probability of dying within one time period is q equal 0.002. The variance among populations in the number that die after one time period is nq times 1 minus q equal 1996. However, if q is a random variable with a mean of 0.002 and a standard deviation of 0.0001, then the variance of expected number of deaths among populations of 1 million individuals is given by this expression, showing that the environmental variation is over 5 times the demographic variation. The difference between demographic and environmental stochasticity for fertility is illustrated by the following example. Suppose that fertility of a particular age class is 1.5 offspring. However, only whole animals are born. Thus, this value of fertility might arise because a single individual produces either 1 or 2 offspring with equal probability. In this case, if there are n individuals reproducing, then the average number of offspring is 1.5n. The variance of the total number of offspring is the sum of the variances for each individual, and because individuals reproduce independently, the variance equals the product of 0.25 and n, which is the variance on fertility due to demographic stochasticity. Alternatively, environmental stochasticity may be present if the level of fertility for the entire age class shifts with changes in the environment. For instance, suppose that fertility is either 1 or 2 with equal probability. The average number of offspring is still 1.5n, but given that all individuals experience either high or low fertility, the variance is now equal to the product of 0.25 in n squared, which is the variance due to environmental stochasticity. The variation in this case is high because 100% of individuals produce either one offspring at the same time or two offspring at the same time. In the demographic case, on average, one individual produces one offspring will be offset by another individual producing two offspring. Given that these two variances differ by a factor of n squared, it is clear that environmental stochasticity will be much more important than demographic stochasticity in this scenario. Environmental variation in vital rates. The pattern of temporal variation in the environment will impact the correlations in vital rate values within and between years. Here, with a schedule of age-specific fecundities, I will illustrate the impact of random or temporally correlated schedules of vital rates on the variance of reproduction. In the case where schedules of fertility are random across years, and thus either two schedules, A or B, are equally likely, there will be four possible combinations of rates, with a 25% chance for each rate to occur on any given time step. These rates are M1A plus M2A equal 50 offspring per day, M1A plus M2B equal 32 offspring per day, M1B plus M2A equal 23 offspring per day, and M1B plus M2B equal 5 offspring per day, with a total of 110 eggs. The average fecundity of a population experiencing these conditions is 110 over 4 equal 27.5 offspring, with a variance of 263.3. In the second case, where the schedules of fertility are correlated over time, then both age classes have rates from the same schedule at each time, with the occurrence of schedules A and B equally likely. The two possibilities are Schedule A equal M1A plus M2A equal 50 offspring per day, and Schedule B equal M1B plus M2B equal 5 offspring per day. A total of 55 offspring. This gives the average fecundity for this case of 55 over 2 equal 27.5, which is the same as the random case, but the variance 506.3 and standard deviation of 22.5. The reason that the variance is higher in the first random case is that on average, half the time, a high rate in one age class is offset by a low rate in the other. Only 25% of the time is fecundity extremely low. In contrast, when the schedules are correlated, the elements within each age are either uniformly high or uniformly low, and the daily variance in vital rates is much greater. Stochastic rate of population growth. Two critical demographic problems emerge from these hypothetical examples. First, how do stochastic vital rates impact population growth rate? For example, how does a twofold difference in daily fecundity change growth rate relative to, say, a fivefold difference? Second, how will the average growth rate differ when individual elements are subject to stochastic processes, i.e. demographic stochasticity, versus when individual schedules are subject to stochastic processes, i.e. environmental stochasticity? Tolter-Picard in 1990 developed a framework for examining these questions, including the formula for computing the stochastic rate of population increase, R subscript S. Note that the notation here is different from what's given in Tolter-Picard in 1990. This parameter is not a strict analog of the deterministic little r because there is an average of several possible rates. The conventional population rate R is a singular rate. The formula for the average population growth rate subject to stochastic rates is given by this equation, where R denotes the intrinsic rate of increase for a Leslie matrix population whose elements are the average of all rates for each element, and C is a term that depends on how the vital rates are correlated as a result of stochasticity. Two general points of stochastic growth rate merit comment. First, the value of RS is never greater than R because the age structure of a population subjected to the changing vital rates is never adjusted to the conditions of the moment. For example, given a rapid change in vital rates, a population of aphids in which the majority of individuals are in the older age classes would not respond as quickly as a population with primarily young individuals. Second, the stochastic growth rate is affected by time filters that modulate variance. For example, long-term growth rates are less affected by large variance in survival in older adults for the same reason that growth rate is affected less by changes in mortality in older adults. This is because these older age groups constitute a small proportion of the total population, and in particular are in the lower reproductive age classes that have low prospects for continued reproduction. Strong and weak ergodicity. Population models can incorporate variable vital rates that vary either stochastically or deterministically. The salient results of population models with fixed vital rates is that they forget their past, and thus exhibit the property referred to as strong ergodicity as age structure and growth rate converge to numerical fixation. Population models with variable rates exhibit weak ergodicity because although the population models also forget their past, they do not converge to constant growth rates and fixed age structures. Weak ergodicity with variable vital rates can be classified in one of two subcategories, either weak stochastic ergodicity or weak deterministic ergodicity. With weak stochastic ergodicity, two populations with identical stochastic rates will exhibit similar long-term patterns of growth and age structure. The key concept for this case is long-term. That is, there will be no similarities between the populations in the short-term patterns due to the stochastic nature of the vital rates. With weak stochastic ergodicity, two populations with identical stochastic rates will exhibit similar long-term patterns of growth and age structure. The key concept here, again, in this case, is long-term. Two populations subject to the same deterministic sequence of vital rates will eventually exhibit identically varying age structures and growth rates independent of differences in their initial conditions. The key concept for this ergodic case is identically varying. I will illustrate these basic ergodicity concepts by showing the results of simulations using demographic data on aphids in which fecundity varies either stochastically or deterministically. The data are shown in this table with age in days from 0 to 28 days in this column, survival in the next column. Reproduction at 5 levels is shown here in each of these columns. Here I show the results of population simulations using the aphid reproductive data and survivorship information. Note in the top set we have population growth rate. In the bottom set, stage structure. The x-axis in all cases is time from 0 to 100 days. Each of the graphs from left to right progress from shorter to longer reproductive cycles. The top rows of each set are the results of the growth rate and stage structure for the deterministic rates, and the bottom rows for each set are the results for stochastic rates of population change. Two important patterns emerge. First, differences between patterns generated by stochastically varying rates and deterministically varying rates are distinct. The former generating large variance but no regularity, and the latter with both large variance in rates as well as regularity in pattern. Second, age structures in populations skewed towards adults due to low growth rates may produce major spikes in growth rates when, either by design, deterministically, or by chance, stochastically, the transition to the reproductive schedule contains the highest rates is abrupt. This ends Module 7.2 on stochastic demography.